story, CMB anisotropies are extremely sensitive to how exactly the universe became neutral. Went from going fully ionized to neutral. So here I'm showing again this ionization fraction starting at 1.16 and going to 0 as a function of time. The purple line is the standard story, and I'm adding artificially a bump in this ionization fraction, 10% bump. And I'm going to move artificially this bump forward in time, and you're going to see how this affects the power spectra of temperature and especially polarization with the CMB. So this is a hugely exaggerated bump. Okay, but the point is that the temperature and especially polarization power spectra are very sensitive to how exactly the universe recombined, even quite late times after the last scattering of CMB photons. Okay, and we will see towards the end of the talk when I talk about primordial black holes. One of the things I'll talk about is that if you have some process that injects energy into the plasma and can ionize the universe a little bit beyond what is expected from the standard calculation, then this will translate to some change in the temperature and polarization power spectra. This is how you can constrain, for example, annihilating dark matter. So Tracy Slatcher, I think, is giving the talk this afternoon. She worked a lot on annihilating dark matter, or primordial black holes. So this is basically through this kind of effect. So what does it mean? So before talking about non-standard physics, the fact that we have such a sensitivity means that we need to understand the theoretical model of recombination very accurately, first of all, and also we need to be able to compute it extremely efficiently so that we can run it multiple times compared to the data and extract the cosmological parameters within the sub-percent precision that I was talking about. So the last time I came here 9 years ago was to explain all the details that go in this code. HiREC, it was just before it was finished. All the physics that goes into modeling recombination to this sub-percent precision. And Jens Kluba and collaborators also wrote a similar code, CosmoREC. Those codes are, the accuracy of this code is estimated to be a few times 10 minus 4, because of course there's always the possibility that there are some physical effects that no one thought about. And they both run in less than 1 second per cosmological model, which I thought would be sufficiently fast to become the new standard code used in cosmological parameter estimation. Now it turns out that the default code that is still used, that was the default code for WMAP, but is still used currently for the Planck data analysis, is the code RecFast, which was written by Sarah Seeger, Dmitry Saselov, and Doug Scott. I think Saselov is still here. I'm not sure if he's in the audience. But I don't think it works in cosmology anymore. So this code does not have all of the physics that is in HiREC and CosmoREC, but it was basically fudged with some fudge function to approximately recover the correct physics in HiREC and CosmoREC. And that was very surprising to me. And so the reason why is, first of all, that the recombination calculation, in contrast with the calculation of the transfer functions of different Fourier modes in the CMB, for those who are familiar with this. So this calculation is highly parallelizable. You can essentially compute every Fourier mode separately. But the calculation of the recombination history is not parallelizable. You have to compute this, and even if it takes 1 second, this 1 second eventually actually becomes the bottleneck of the calculation. So 1 second is still too slow, apparently. And secondly, well, once you do these fudge functions, the accuracy of RecFast becomes good enough for Planck. But I don't think anyone has the question of whether it would be good enough, how far in the future, how precise instruments can you analyze with these fudge functions. So my student Nanoom Lee and I have been working on this new version of HiREC, which should be released soon. So it's based on an effective 4-level atom model, which is basically captures exactly the dynamics of recombination at low redshift without, it basically gets rid of some of the fudges in RecFast, not all of them. The part that takes time is the radiative transfer calculation that is in HiREC. So this we do have to account for with some correction function that we compute from the full HiREC. But we also compute the derivatives of the correction function with respect to cosmological parameters. So basically, Nanoom has written a code which is as accurate as HiREC and runs in 10 milliseconds per cosmology. And this is actually faster than RecFast. hopefully this will be used for future cosmological parameter estimates. So this is to give you an idea of how biased you could get if you were using a code which is not quite on par for the accuracy. So here, these are the error ellipses from the Planck current cosmological parameter measurements. So Nanoom, picked randomly some Gaussian distributed 10,000 samples or so of cosmological parameters as like a fake universe, and then extracted from a simple Fisher analysis what would be the biases in the cosmological parameters if you analyzed this data with an inaccurate recombination code. So this is showing this this is comparing, this is the bias that results from the difference between the full hierarch and this Swift hierarch that we have just written. And in comparison, this is the biases in red that you would get if you were using the RecFast code. This is for a cosmic variance limited experiment up to L of 5,000, so this is a highly futuristic experiment. But the point is, eventually you have to stop doing fudges and you have to use an accurate recombination history within a few parts in 10 to the 4, and hopefully this code now is not only accurate enough, but also fast enough to become, I hope, the standard use for future CMB analysis. Okay, so this was a brief overview of the CMB with some shameless advertisement in the end. Let me now move to dark matter. Are there any questions?
So very simple question. Can you go back to the previous slide? From this plot, is this like easy to imagine why in some of the parameters, like for example theta s, the errors that you get if you use RecFast is much higher than your sleep one, or?
For this, I would have to show you the exact shape of the bias in the recombination history, and then we would have to understand it. But so there's not like an easy way to see it. Yeah, I don't have an easy answer for this. Yep.
Yeah, so eventually we'll have to move to this, like in a timeline.
I mean, I think we can move to it right now because so if you use RecFast, it's been basically calibrated for just one single cosmology, the fiducial cosmology. But if you want to add any non-standard cosmology, every time in the Planck publications they say, well, we actually checked that it's still okay to use this fudge RecFast. So why not just use the the real deal? So I think, yeah. But this, so for stage 4, it would be like marginal. You can still use RecFast and be okay, like within, I don't know, 0.3 sigma or something like this. So yeah. You could keep doing it, but it's not very aesthetically pleasing. All right, so let me talk about dark matter, how one can test dark matter particles if they interact with standard model particles with the CMB. So, of course, one of the main avenues to test this is through direct detection experiments. Now, why is the CMB and in general astrophysical and cosmological probes interesting is that they are complementary to direct detection experiments in several ways. First of all, they can probe a range of mass, which is not easily accessible to most direct detection experiments. Typically, those are upper limits from direct detection experiments on the cross-section of dark matter with nuclei, and typically they hit a wall around a GeV or so because the dark matter no longer has enough kinetic energy to impart sufficient recoil to the nuclei. The CMB and in general astrophysical probes are very sensitive to this. These experiments have some sort of upper limit in the cross-section because the dark matter, if it interacts too much, may not even reach the detector and may have lost too much kinetic energy before it reaches the detector. And of course, they have very different uncertainties. So for example, direct detection experiments, to interpret the results in terms of upper limits to the cross-section, you need to fold in your assumption about the velocity distribution of dark matter on Earth, around Earth. And in the case of the CMB, things are a lot cleaner. This is just to illustrate that there are still some regions of parameter space which are not probed by either this direct detection experiments or the CMB. And so if you can get better limits with the CMB, you can presumably cover more parameter space and maybe exclude more dark matter models. So I told you there was two aspects in the CMB. There's the frequency spectrum and there's the anisotropy. So let me briefly talk about the frequency spectrum and how this can be sensitive to dark matter interactions. So if you have your hot bath of photons and baryons, and on the other hand, you have your bath of cold dark matter. Now, if you assume that, say, dark matter can elastically scatter either directly with the photons or with any one of the particles in this hot bath, it can scatter with the electrons or protons, then you will put these two thermal baths in thermal contact, and there will be some net heat flow from the hot stuff to the cold stuff. And so the dark matter would act as a heat sink for the photon baryon plasma. So if you turn this around, you can use this, given the upper limits to the CMB distortions away from the blackbody spectrum, which are, as I said, a few parts in 10 to the 4 currently from COBE-5RS. You can already put some upper limits as to how strongly the dark matter can interact with protons, electrons, or photons. Those don't go to very high masses because if you have, for a too large dark matter mass, you have too few dark matter particles and they cannot extract a lot of heat. And this is just illustrating that if one could gain, in this case, 4 orders of magnitude in spectral distortion sensitivity, as some experiments are planned, and as there is the technology, presumably, to do this, then you could extend these limits much farther in mass, reaching up to a GeV and complementing direct detection experiments. As a CODA, so this is something I worked on a few years ago with Jens Kluber and Martin Markowski. This was a short paper where I made a lot of approximations, and I realized that some of them were a bit too simplistic. Luckily, it went in the right way. So these forecasts are actually extremely conservative. If you do things a little bit more carefully, it turns out that an experiment like PIXI would be sensitive to much, much smaller cross-sections than what I first had calculated.